Well, hello everybody. Today we're going to talk about 8.7, the indeterminate forms and L'Hopital's rule. And L'Hopital's rule is a way to deal with the indeterminate forms when we end up with like 0 over 0 or infinity over infinity or something like that. Right. So, for example, here is an example of what might happen. The top example up here, we can factor and we can simplify it, and this is kind of how we dealt with limits before. So if I was to factor the top, I'd get e to the x minus 1 times e to the x plus 1, and then it would be over e to the x minus 1. And we'd have our limit here, limit as x goes to 0. But when I do this, I can reduce out the e to the x minus 1s, and so now I have this limit as x goes to 0 of e to the x plus 1, which I can actually put in 0, which will kick out a value of 2, which would make sense because we're basically dealing with, as we're approaching 0, what value are we crossing the x-axis at? And if you remember, e to the x looks like this. It crosses at 1, but when I add the addition of plus 1 to it, it actually pushes it up here. So as we approach 0 from both sides, we should be approaching the value of 2 because that would be the transformed function. All right. Down here, though, we can't factor, we can't do any of that stuff, so we can't rewrite it in any way, shape, or form. So we don't have a way right now until we don't have a way to simplify this. All right. So this is where L'Hopital comes in. And L'Hopital talks about the functions. If you have a fraction and you're doing a limit as it approaches a value or infinity or something like that, if you have two functions top and bottom of a fraction, and you try to find the limit, but you get the indeterminate form, like 0 of 0, infinity, or some other weird form of it, then you will you can bypass this by taking the derivative of the top and the derivative of the bottom, and then substituting in the c value, and where these guys go will be the limit of the original functions. Right? And so that's kind of where we're going. And the only thing we really have to be careful of is that g of x. We don't want that g prime of x to become 0. We want it to become some kind of value. All right, so let's try it. Here we go. So our first example here, we have if I substitute 0, and we always start with direct substitution, putting 0 into this function will give me e to the 0 minus 1 over 0, which is 1 minus 1. So we get 0 over 0. So that means that we have to do a little more work. But L'Hopital helped us out a lot because he said that if we were to take the derivative of the top, which the derivative of the top will be 2e to the 2x, and the derivative of the bottom is 1. And typically our goal is to get the bottom to equal some value, or the top to equal some value other than some function. And when this happens, then we can take the limit. And so now if I take the limit, of this thing, putting in 0, doing my direct substitution, I get 2e to the 0 over 1, which kicks out the value of 2, which makes us much happier, and therefore there is our limit of this original function. All right, so let's try another example. Another example is this, and again, we are going to substitute in infinity, and if you remember anything about the graph of ln of x, it looks something like this, and you'll notice that as it goes off towards infinity, the graph slowly grows towards infinity, so then the top is infinity. The other graph that we have is e to the x, which might look something like this, and that one's fairly obvious that we're going to be going off to infinity if we were putting in infinity. So again, that makes us kind of sad. So we're going to have to do something else to make it a little bit better for us. And L'Hopital gave us an idea that if we were to take the derivative of the top and the derivative of the bottom, then we should end up with a value. We can end up with a value for these derivatives that would be the same as the value of the limit of the original function. All right, so if I take the derivative of the top of ln of x, I get 1 over x. The derivative of the bottom is 1. So basically, I am taking the derivative. If I put infinity in for this, I get 0 on top and 1 on the bottom, which gives me a value of 0, which makes us happy again. All right, so that's really what we're looking for. All right, we have another one here. This one, well, we might have to apply L'Hopital's rule more than once, and that is always an option. So in this case, I'm looking at this function, and I would start with direct substitution. And basically, the top, if I have, e to the x squared, it looks something like that, which is off a little bit on the axes. But as you can see, as I go to negative infinity, the graph itself goes off to positive infinity. And on the bottom here, if I have e to the negative x, well, it would just be the reflection of the other graph. And so as we go towards negative infinity down here, this graph is shooting off to infinity. So we are stuck with infinity over infinity, our indeterminate form. So L'Hopital gave us the way that if we were to take the derivative of the top, which would give us 2x, and the derivative of the bottom, which would give us negative e to the negative x. And so in this case, again, we can try infinity, but remember that e to the 2x looks something like that. So as x goes to, as x is going to negative infinity, we're going down to negative infinity. But then on the bottom, e to the negative x is a reflection of this other graph, so it's going to look something like this. And so as we go to negative infinity, we're going down to negative infinity again. So we're stuck with this, and that's still not good for us. So we are going to apply L'Hopital's rule one more time, and we will see if that helps us. And so as we do this, there's a negative sign there, sorry. Adjust it up. But if I take the derivative of the top, I get 2, which is a value which is very helpful. And again, then we have e to the negative x. So the top is a constant, so no matter what, that top will always be 2. And on the bottom here, when we go to infinity, for e to the, if we go to negative infinity, yes, as we go to negative infinity, this thing goes off to positive infinity. But remember that we're basically dividing by infinity, which gives us the value of 0, which makes us happy again, unlike the one that was making us sad. So we end up with, as we do these guys, our goal, we're going to end up with a 0 quite a bit as we go through these, but don't be surprised if you get values as well. All right, so our next example is this time I'm taking 0 times infinity, and what is that going to get us? Well, that doesn't get us 0, but we can do some manipulating of this function, the setup of this, to give us a little bit better view of what's happening here, and again, and how it fits into L'Hopital's rule. Well, we've got the square root of x and e to the x when I move the negative sign down to the bottom. So in this case, putting 0 in, remember that the square root of x is a function that looks like this. So as we go off to infinity on my x values, my y values go off to infinity. And e to the x itself looks like this. So as we follow the x values to infinity, my y values go off to infinity. So that gives me infinity over infinity, and that makes me sad again. All right, so now we are going to we'll try apply L'Hopital's rule, which says let's take the derivative of the top as a separate function, which gives us 1 over 2 root x, and the derivative of the bottom is e to the x. And so I'm going to manipulate this guy just a little bit, since this looks really goofy with it being this way. And this would work even if I substituted in 1 over 2 root x. If I substitute in infinity, this guy is going to give me 0 on top, and on the bottom, as this thing goes off to infinity, this thing is going to give me basically, well, I don't like talking like that way. Let's just manipulate it. Let's just change it up a little bit. I don't like the looks of this. So to talk about it, it makes more sense if we rewrite it as 2 root x e to the x. So both of these guys go off to infinity, and so basically we're dividing 1 by infinity, which gives us 0, which is another value that will help us out and make us happy again. All right. So moving along here, now if we take 1 to the infinity power, because basically if I substitute in, this guy would become 0, and this is infinity. So 1 to the infinity power, where is that guy going to go? Well, we have to remember some things that we did before, like we did an example where we were taking x to the x power, y equal to x to the x power, and we didn't deal with it that way. We dealt with it with the natural log of y equals x times the natural log of x, where I push the exponent out in front of the natural log using my natural log rules. Well, this is the same idea, and that's the way I'm going to go about this. So I'm going to natural log both sides. And when I natural log both sides of this, I get ln of the limit as x goes to infinity of 1 plus 1 over x to the x. So I get that. And so then I'm going to kind of move things around a little bit. I'm going to leave the ln of y here. I'm going to move my limit as x goes to infinity out, and I'm going to take this exponent and put it out front of this function. So it's going to be x ln of 1 plus 1 over x. All right, now I'm going to take the derivative. So in this case, to make it look like L'Hopital's rule, I'm going to manipulate this a little bit. And what I'm going to do is I'm going to move this x and I'm going to change its form, and it's going to look really kind of weird, but it is just a way we can manipulate it. X can be written as 1 over x, because remember, if you flip it over, it'd multiply up to the top and all that stuff. So we end up with something that looks like this. So now, if we apply L'Hopital's rule to this, I'm going to take the derivative of, so I'm just going to kind of write over here and say, what if my f of x was 1 plus 1 over x? Well, if I take the derivative of that guy, I get negative 1 over x, x squared. And so that's what I get when I take the derivative of that. It's also the same as if I take the derivative of 1 over x, I get that. And so when I do this, when I rewrite this, I'm just taking the limit in the fraction to get a value over here. So the top becomes, well, u prime is this thing right here, so it's negative 1 over x squared. I'm dividing it by, I would be dividing it by using my rules of natural logs, dividing by this, but I'm going to write it a little bit different, and I'm going to write it as 1 over 1 plus 1 over x. So if these guys got multiplied together, they would look just like the derivative of this. And then on the bottom, I get negative 1 over x squared. Well, good news is that these two reduce out of the problem. That helps us simplify this a little bit more. And so ln of y is going to equal to the limit as x goes to infinity of 1 over 1 plus 1 over x. Well, if I take this to infinity, it looks like I'm going to get a value of 1. So this limit now is workable, and so ln of y is equal to 1. And since I got ln of y equals 1, I can go base e to both sides to get rid of it, so I can find out what y is equal to, and you can find out that y is equal to e to the first, which if we go back up and look at our graph, you can kind of see that this is somewhere between 2 and 3, where my horizontal line appears, and that looks like it's probably about the value of e is really what we're looking at for this function. All right. And so I've got one more example we're going to deal with. What happens if we have sine of x to the x? And so now we're taking 0 to the 0 power. And same idea is going to happen with this because we see this exponent of x. And so we're going to kind of have to work our way around this. So I'm going to say this guy again is y equals. So if I natural log both sides, I get the natural log of the limit as x goes to 0 to the right-hand side of sine of x to the x power. Well, with that being said, I can throw the x out front, move my limit around a little bit, and so I'm just going to clean this up and rewrite this as x goes to 0 from the right-hand side of x ln of sine of x. And the majority of this is just trying to manipulate this thing to get it into a form that when we take the derivatives of these things or whatever, things work out a little bit better for us. So again, I'm still going to try to take my limit as x goes to 0. And remember, if we substitute these in, this is what we'd get up above. So I'm going to rewrite this as ln of sine of x over 1 over x. And so now if I take the derivative, so if I said f of x was ln of sine of x, when I took the derivative of that, I will be left with the derivative of the inside is basically u prime over u would be cosine of x over sine of x, also known as cotangent of x. And on the bottom, if I had g of x was equal to 1 over x, g prime of x, prime there, is equal to negative 1 over x squared. All right, so that's what we get when we take the derivatives of the top and bottom, because we're still stuck with zero. This is zero on the bottom, it's zero on the top, so we're stuck with that until we take the derivatives. So we're going to get this ln as the limit as x goes to 0 to the right-hand side. The top becomes cotangent of x divided by -1 over x squared. So well, let's manipulate this. The 1 over x squared could be flipped up to the top, and cotangent is the flip of tangent. So why don't we flip-flop these guys' places at this point in time, and maybe we will be in a better spot for what we're looking for. All right, so if I flip-flop these places, I get -x squared, and on the bottom, I have tangent of x. All right, well, great. In this case, I can still put in 0, and I get 0 over 0, so I have to do L'Hopital's rule one more time. So the ln of y as my limit as x goes to 0 from the right-hand side, derivative of the top is -2x. Derivative of the bottom is secant squared x. And so in this case, if I'm putting 0 in for secant squared, well, secant squared kind of goes off to infinity, because if you remember, secant itself is the opposite of cosine, and so it does something like this. This is secant around 0, 0 to pi over 2, and this is -pi over 2. And so as we're approaching 0, this thing is approaching, this secant squared is approaching 0 as well. So in this case, this will have a value, whatever it may be, secant squared, wherever it is. As we approach 0 from both sides, we're going to get a value down here of something. And we would have to find out what it is, but in this case, when we do this, we're going to be left with 0 as my limit as we approach this, because the top is 0, and this guy is going to be a value, so it's going to be 0 over a value, which is 0. So now I'm left with ln of y equaling 0, and like the previous case, if we go base e on both sides, basically y is going to equal 1, and that's what we were looking for our limit in this case. So this concludes L'Hopital's rule. We will do more practice on this very, very soon.